All right, let's look at differentials. All right, so remember that the derivative notation. Typically we use f prime of x, right? But there's another alternative notation which was dy over dx, right? And the dy and the dx are called the differentials, right? And remember that this is a derivative, just a limit, right? Limit of the difference quotient. So one way to write it is we are taking a limit as delta x approaches 0, delta y over delta x. So this is another way to write that, right? So for small delta x, you can see that the dy over dx are very close to delta y over delta x. So we have dy over dx can be approximated by delta y over delta x, or the other way around. We can approximate dy over dx by delta y over delta x by dy over dx. All right, so in this case, I'm going to set dx and delta x equal to each other, right? Then you can see that dy and delta y are very close to each other, right? And so we can approximate the delta y using a differential dy. And the dy can be found by doing this. This is actually treated like a fraction. And from this equation, we can simply multiply both sides by dx. So you're going to get the dy is really the same thing as f prime of x times dx. All right? So let's do a concrete example. All right? Let's say if you have a function y is equal to arctangent of e to the x squared. And we want to find dy. All right? So we can just simply take the derivative. So you have dy over dx. Right, so derivative of arctangent is 1 over x squared, right? So you have a 1 over 1 plus x squared. So 1 over 1 plus, all right, instead of x, that guy's squared. So you have a e to the, I'm going to just square here, 2x squared. All right, then multiply by the derivative inside, which is e to the x squared, multiplied by derivative of x squared, which is 2x. All right, so what you can do is just simply multiply both sides by dx. So we have a dy is equal to, let's clean this up. So I'm going to put the 2x e to the x squared on top. All right, that will take care of this guy and that guy, and I'll probably 1 too. All right, then you have the 1 plus 2x e to the 2x squared. So 1 plus e to the 2x squared. Then we have to multiply by dx. So you just have to put dx at the end. All right, so this is the differential dy. So if you want to find dy, all you have to do is take the derivative and put dy at the end. All right, so geometrically, we can use this differential to approximate the delta y. All right, so here is the geometrical representation of dy and the delta y. All right, so we're setting dx and delta x equal to each other in this case here. All right, so what is dy? Well, actually, let's do delta y. All right, delta y is simply the difference in y value. So you're starting from this value right here. So let's say this is the original value, right? And then you move delta x, and here's the new y value right here. So it's just a difference in a function value. So here, so this is the delta y, right? So that's the actual difference in y value, right? And the dy, on the other hand, is a little bit different. So dy is actually, as you can see, it's the slope of the tangent line times the run, basically, right? So which gives you the rise. So here, dy represents only this much right here, right? So this is dy, right? But for small delta x value or dx value, delta y and dy, so, so for small dx or d delta x, we can see that the delta y is very close to dy, right? So what you can do is, so delta y is the actual difference in y value. Dy is actually the run of the tangent line, the slope of the tangent line, right? So we can approximate the delta y using dy, right? And in the next example, I'm going to use this differential dy to approximate the value of delta y. All right, that's it. I hope that this was clear.